All right, let's talk about remote sensing, satellite imagery in particular. So first of all, real quick, who we are. So COSMIQ is a small lab based in Virginia. We're actually not-for-profit. Do mostly applied research, computer vision, geospatial analytics, mapping. All of our efforts are open source, actually. Do a bunch of market analysis as well. And then SpaceNet is one of our primary efforts, which is something that's explicitly modeled off of ImageNet, and something that has been pretty successful. So this isn't the focus of the talk, but I just wanted to briefly talk about SpaceNet since it might be of interest to folks in the audience, since it is an open source project. But the foundation is labeled Datasets. We have 6 cities and over 20,000 kilometers of imagery released at high resolution. 800,000 building footprints, 10,000 kilometers of roads. These are all hand-labeled by expert labelers. And we run competitions with this. Again, this is very much the ImageNet model. We're very appreciative of what they've done to kind of advance the computer vision community. And we're trying to do something similar in our little way for kind of the remote sensing domain. All the algorithms, the winning algorithms for this are open source. So if anyone's curious, they're up on GitHub. So go take a look. And then a lot of our effort has actually been software tools because the translation from geo to computer vision is something that's still non-trivial in many cases. And this is something, of course, that we couldn't have done without our partners, so thanks to them, AWS, Intel Digital Globe, and Radiant Solutions. So what do we actually care about for this talk? What if we want to find objects at multiple scales in satellite imagery? So if we're doing this at multiple scales, multiple sensors, this is actually quite a bit of a different problem than what you might get from an ImageNet, where you're trying to find maybe a few largish objects, such as dogs or cats in ImageNet. And there's a few challenges, right? One, probably the primary one, being that objects are often very small. 10 pixels in size is not uncommon, can be even smaller than that. They're also rotated about the unit circle, meaning they can have any orientation or heading. Trees are always pointing straight up, pretty much, right, in ImageNet. That's not true here, since you're looking usually straight down. There's a relative lack of training data, though there are efforts, such as SpaceNet, that are trying to alleviate that problem. You have enormous search areas, right? So, often for things like ImageNet or COCO, you have an extent of maybe up to 500 pixels on a side. For these images, a single image will be hundreds of megapixels. So this is quite a bit of a scale here. And the other thing is geo is still kind of hard, right? Even something as simple, seemingly as simple, as transforming lat long to pixel coordinates can be annoying and time-consuming. There are things that actually make life a little bit easier, such as the physical and pixel scales of objects are well known. And what I mean by this is that you know your sensor very well, right? It's a satellite in orbit, or maybe it's a drone. You know that very well. You know the distance to your objects. You know the size. So that actually makes life a little bit easier in some sense. And there's a relatively low variation in observation angle. Usually you're looking more or less straight down. There are counterexamples to that, but for this case, we'll be kind of considering the case where you're looking straight down. One further variable is deception. So this is something I couldn't resist putting in here. This is a screenshot from the New York Times showing the inflatable aircraft Russia uses to try and spoof our analysts. So this is something you're always going to have to deal with when you're trying to find things from overhead. So kind of first of all, I'll give kind of a bit of a baseline of how you can start looking for objects. So one way, of course, is to have a feature descriptor and tie this to a classifier, run this with a sliding window, right? So the HOG, the histogram of ordinate gradients, was a variant of this, at least, was the best model prior to 2012, right? So this, if you look at ImageNet way back when, some variant of the HOG was the best performing model. Of course, then AlexNet came along, and we had the deep learning revolution, and this is a bit backwater now. But it's a good place to start, just to start looking at. And if you do this, right, so the idea is, of course, you just have a sliding window. You'd go across a very large satellite image. Each time you see a boat, in this case, we'll classify it, say boat, no boat. Maybe the heading as well, if you really want to do something a little bit more interesting. But this is a pretty low overhead approach, pretty simple to understand. And if you kind of look at how this works, in some scenarios, it actually works quite well. So on the right here, in open water, actually doing really well at finding the boats, right? It's high contrast, very uniform background. Something like a harbor on the left is a little trickier, right? They're overlapping bounding boxes. Things are very densely clustered, so it's a bit harder. And where we really start to fall down is where we have non-uniform background. So this is another one of the shots I like. This is actually one of the islands in the South China Sea that's being built up. And you can see there's just a lot of detections over land because there's lots of linear features that the model's confusing. And so this is where, I'll probably not have to convince anyone in the room that deep learning has some value, right? And the other thing is that sliding windows just don't scale to this kind of problem, right? We have millions of small image chips we have to look at if we just want to do a yes/no classifier. So this course brings us to deep learning, and we let convolutional neural networks pull out the features we care about, identify objects of interest. Of course, then we need a GPU, so we can't just run it on a laptop. But again, of course, I don't think I need to convince anyone in the room why GPUs are interesting. Of course, they will run on a CPU, but at a couple of orders of magnitude slower. So if we are trying to get to something that's more advanced, simple sliding windows don't really work for the scale we're talking about. But there are rapid open source frameworks for object detection, right? And there's a number. Probably the three that are the most commonly used right now are YOLO, SSD, faster RCN, and RFCN. These are all frameworks that have competed at things like ImageNet or COCO and done quite well. So I'll first mention a little bit about YOLO. So this is an object detection framework from 2016 or so. It uses a single convolutional neural network that predicts classes and bounding boxes, encodes contextual background information. It's Google Net inspired architecture, and it's real-time speed. So one of the things is it's actually built in C, so that makes it pretty quick. Also makes it a little harder to work with, but it gives it some good speed. And essentially what it does, right, so if you look at this image in the top right, you take an input image, breaking up into a grid, looking for bounding boxes and confidences, looking at class probabilities, and your final output then is the bounding boxes on the right of dog, bike, and car, of course, right? And does pretty well again, but there's a few limitations. These are quotes from the actual author. And it struggles with small objects in groups, such as flocks of birds. It also struggles to generalize to new or unusual aspect ratios or configurations. And it uses relatively coarse features due to the many downsampling layers. So all three of these limitations are things that could plausibly crop up with satellite imagery, right? Where you can have very small objects that are very densely clustered in kind of weird configurations because there's things rotated all over the place. And then one thing that's true kind of for all the frameworks is that the maximum input size is maybe 600 pixels. You could maybe stretch it to 900 on the side, but not much more than that, because if you're looking at, say, 10 gigs of GPU memory, you just can't get much more than that into the actual system. So shortly after YOLO, the TensorFlow Object Detection API came out. This is a great paper, and it's kind of a collection of a lot of the other frameworks. So SSD, fast RCN, and RFCN, they're adding to it all the time. Retina Net, for example. And so this is something that really lowered the barrier of entry for getting started with object detection. A lot of the challenges here are the same as for YOLO, right? It's not really designed for super small objects. They're really densely clustered. But it is a really good resource. So this brings us to satellite imagery. So we kind of saw these problems, and we said, OK, what can we do? So we developed the Satellite Imagery Multiscale Rapid Detection with Windowed Networks, or SimmerDown. So this is a unified framework that extends both YOLO and the TensorFlow Object Detection API. And we train an ensemble of networks, and we test on arbitrary image sizes. And I'll get into how that works as we go forward. So how do we address some of the shortcomings of the current architectures? So for something like small groups or densely clustered objects, you can look for a new network architecture with, say, denser final layers. Or you can upsample if you really want to look for those really closely packed objects. Let me back up for a second. If you look at the top image on the left, so this is just a small image chip, right? So even if you just care about a tiny image chip and you're looking for cars, train a model, find cars, and then you test it on this image in the top left. you're still doing a very poor job of finding cars, right? This is standard YOLO in this case. And the reason is because they're just too densely clustered. And so just applying this standard architecture here does not work very well. Conversely, if you just take the image, the whole image, and just shove it in, and that's the bottom in green, you see nothing at all because the features are way too small. So you can't just put it in blindly. And then coarse features, of course, you can do this upsampling. In the green, the bottom box in the middle there, the maximum input image size of 600 pixels really is the kind of primary constraint for satellite imagery. And for that, we have to kind of intelligently partition and recombine these large test images. And running Ensemble at multiple scales is something that we'll see is pretty crucial later on. And I should mention, right, satellite imagery is the application we've chosen. That's kind of what we're interested in. But this is something that you could do for any large imagery, right? So of course, this same approach would, in theory, apply to biological images, where you have very small objects of interest in a very high density and just high resolution image. So what's the procedure? Of course, we extract images and labels. We can rotate and augment the images. Rotation is something you don't necessarily do all the time, right, with imagery for your pre-processing, but we can do it here. We build YOLO image list and the TF record for the TensorFlow, train the ensemble of models. And for testing, right, we partition a large test image, infer on those small image chips. We stitch it back together into a global prediction set, execute non-max suppression, which is the image we're showing here on the right, and then evaluate metrics, such as F1 or mean average precision. So in this case, training data, we're collecting them from small chips out of large images from both digital globe and planet. So for those who aren't familiar, digital globe is very high resolution imagery, either 30 centimeter or 50 centimeter resolution. What that means is each pixel in the image is that size on the ground, so 30 centimeters. Planet is something that's much different, so that's about 3.5 meters per pixel, very much lower resolution. So we use both those input image data sets, and labels, of course, a bounding box and in a category ID for each object. We focus on 4 categories initially: airplanes, top right, boats, top left, cars, that's bottom left, and then airports is bottom right. So that's obviously a very different scale, right? Airports is a lot larger than a car. Training is 2 to 3 days on kind of typical consumer-grade hardware per model. So the first thing we tried was, let's just build one global model, right? Throw them all in, train a model, and see what happens. And what we saw was actually really poor performance, because things like linear features such as highways get easily confused with a runway. And that's what you see here in this image on the right, where these cyan boxes are erroneously identifying runways out of linear features. And there's plenty of ways you could try and solve this, but the simplest one is, let's just run on 2 different scales, right? We know the scale of the object that we're looking at. And so we can say, for objects like vehicles, let's look at 200-meter scales. This is airplanes, boats, and cars. And for something like airports, we'll look at 2,000 meters. And looking at this additional scale at 2,000 meters really doesn't impact runtime, right? Because there's so few 2,000-meter chips in a large image. So it doesn't really have any impact on runtime, which is nice. So with this in mind, what do we actually run? Well, we look at 6 different models. So the 4 sweet spot models from the TensorFlow paper were faster RCNN, which used the ResNet 101 backbone, RFCN using the same backbone, and then SSD using both the Inception v2 and the MobileNet backbone, as well as YOLO, and then YOLT, which is something that we developed, which is an enhanced architecture for YOLO that's really kind of geared towards this problem set of satellite imagery. We do somewhat of a hyperparameter grid search to make sure that we're actually testing the different hyperparameters in all these different models, and we're not getting kind of myopic. And then we use this test train data on the right. So airports, actually very little data there. That's the best we could do, but around 50 objects total, that's it. Airplanes, just a couple hundred. Boats, that's a couple hundred. These are all things that we labeled internally. Cars is actually something that we were able to find an external data set for. We'll talk about that a little bit more later, actually. That's a much larger data set, around 30,000 cars that are labeled. So what are the results? So just first a few pretty pictures, because everyone loves that. Here's finding cars in a test image. This is over Salt Lake City, I believe. Doing a decent job, right? Now let's look at what we get from airports. So actually here, there's a couple positive examples. And on the right, you actually see it's pulling out this runway. It's kind of hard to see, I think, to me, but it's doing a decent job. One on the left is another one that I find amusing. This is a runway built on another one of the islands in the South China Sea. So there's lots going on down there. And then you can combine this, right? You can do vehicles and infrastructure. And so here we're showing an airport, and we're seeing the actual runway getting pulled out by this orange box. And then on the right, you see some some red boxes. Those are boats that are anchored offshore. And then the blue are the aircraft. So it's doing a decent job. Of course, it's not perfect, wouldn't claim that, but again, decent job. Pretty pictures are nice, but we're not going to just stop there and call it good. What metrics are we actually using to see how well this does? So we'll use IOU, intersection over union, to measure true and false positives. Anything over an IOU of 0.5, consider true positives pretty standard. That's what we use as well. And then from these true and false positive negatives, you can compute precision and recall. And then you can roll those up into aggregate scores like F1, which is the harmonic mean of precision recall, or mean average precision, which is the area under the precision recall curve. So we'll look at F1 and mean average precision going forward. So let's go back for a second to look at boats, right? So remember we had this HOG descriptor, which works really well in open water, but seems to fall apart. So on the left here is what this classical approach gives you. It might be hard to see, but an F1 is 0.28 for this. So for the same image, if we apply this deep learning methodology and simmer down, we get an F1 of 0.81. So obviously a significant improvement there. If we look at the mean average precision scores, these are the curves for the 6 models. I'll skip over this. It's a bit hard to see probably. Spend a little more time here. And on the left is one of the TensorFlow models, SSD. And it seems to really struggle with rarer objects. So this orange curve is airports. And for SSD, right, we only had 30-some training examples. It's having a really tough time finding the airports, right? The average precision for airports is 0.07. Whereas in the middle, this plot is for the YOLT architecture. And it's doing a much better job of finding all the objects. You also can oversample. So if you cut your window size down even farther, you can get actually a boost for really dense objects. This will come at a runtime cost, right? You're looking at more windows, and so you're much slower. But if accuracy is paramount, this is something you can do, and that's what we're showing with this curve on the right. And if we look at the speed-performance trade-off, at least for this study, we were kind of surprised to see there actually isn't one, in the sense that the YOLT model actually outperforms both in inference rate, which is the x-axis here, and mean average precision. So inference rate here is looking at about 0.44 square kilometers per second. So that's going along pretty quick. Mean average precision for this data set is around 0.7 for the YOLT model. So the TensorFlow models seem to just really struggle here. Still kind of dig it in, but the most likely scenario and what we've seen so far is I think they just need a lot more training data, and they're just a little less flexible. So there's coarse hyperparameters that you could also, there's more hyperparameters that could be tweaked, but we didn't need to tweak those for the YOLO/YOLT model, so it seems a little more flexible in this case. So let's on to performance plots. So this is kind of something similar to what I showed earlier and what you might typically see. We see this a lot in our domain of people showing us pictures like, oh, cool, we found all the cars. And to me initially, like, yeah, this looks pretty good. But the problem here is it's really hard to kind of spot the errors. To me, there's very few obvious errors in this image. So one thing that we've started to do is we color code everything, right? This is a test image, and we have the actual ground truth in this case. So what we do is we just color code ground truth as blue, true positive as green, false positive as red, and false negative as yellow. And so a lot of green here, which is good, but it's a lot easier to see that you've got a couple false negatives and a few false positives, especially in, let's see if I can get this to work. There's a few false positives kind of hidden in there. You just have too many predictions, right? This is something that's really hard to see if you just plot the bounding boxes. So this is something that, again, it doesn't look as pretty if you're trying to sell something, but we're not trying to sell something. So hey, it's kind of nice to know where your failures are. Of course, once in a while you get an error where you have something like an air conditioning unit gets popped out. But all told, this is still doing decently well. Another thing that people do, right, very thankfully, is often put the confidence level. So you have something like an elephant, and you say elephant with 99% confidence, right? This works really well for ImageNet style imagery. If you do the same thing for satellite imagery, which we've done here, it's just a mess, right? This is our cars, and after the car, we've put the confidence level, and it just, you can't really tell what's going on. So one option here, there's many options, but one option is to scale the bounding box opacity with confidence level, right? So what we've done here is, in this case, this model is showing cars as green, buses as blue, and airplanes as orange. And so on the left here, we see that a lot of these cars are pretty bright green because there's high confidence. But then in this case, right, this is actually an error, right? This is a false positive. It's a low confidence, though, so something that we could use maybe going forward. And also on the right side here, right, the bounding box around the aircraft is quite bright, right? We're pretty confident in that. Right below the aircraft, again, there's a structure that I'm not even sure if it's a bust or not, but again, it's pretty transparent, and so we color that with a low opacity, so we kind of indicate if we're confident or not. And this works pretty well in these really dense environments. So we have this tool that is fairly flexible at finding objects fairly rapidly. And what can we do? So we have this kind of rather small data set, and we saw some decent results, actually. But we can actually expand it, right? So kind of after the study was completed, the XView data set kind of came out, which is 50+ object classes, quite a few objects, a million-ish objects, primarily cars, trucks, and buildings. But then you have maybe a couple hundred dump trucks, things like that. So there's also smaller classes. So that's what kind of what's shown here is if you train a model there and look at a test image, this is obviously an airport, and we're pulling out airplanes, buses, cars, et cetera, for this. Buildings are not really the right thing to do with this. We'll get into that a little bit more later, but it's something that's possible. Another thing you can do is, so you have a tool, this one or any other tool, that lets you look at objects, and you can explore how sensor resolution impacts performance for object detection. So this is something that actually could be interesting if you do it right, because this could help inform actually how you build or buy a sensor. So what we've done here is we're looking for cars, and we've plotted the GSD, this ground sample distance, aka resolution. And so this 30 centimeter resolution is what you get from digital globe, and then right around here is what you get from planet. And then F1 score for car detection here on the y-axis. And we have this curve, right, of how things degrade. And you can see, right, so if you want to find cars and you want, say, at least a 70% accuracy, all right, then you kind of have an idea of what sensor you might need. And then we can also take a look at what's the object pixel size, right? So this isn't just a resolution question, but how big are the objects in pixels? And if you look at just say you just want the number of cars, right? You don't even care about finding them. You don't care about the F1. You just want to say how many cars are in this region, right? This is one of the typical use cases people use for satellite imagery analytics of how you might make money, right? Let's count cars in a Target parking lot to see how well Target's doing for this quarter, right? So what if you care just about counting those cars? Well, at least for this data set and this study, you don't need that great imagery, right? If you only have, say, a 5-pixel extent of your object, you can do a pretty good job of counting those cars, right? So this is the ratio. So 1 would be you're getting the exact number of cars. So you're doing a pretty good job. The exact numbers here aren't that important. This is more illustrative of kind of what you can do with this tool because, well, all right, I'll be a little transparent here. When I started kind of working on this, I really wanted to try and track objects. Right? Let's track moving objects from satellite imagery. Didn't take too long to realize, A, that data doesn't exist, and B, there aren't really great tools to even find them in the first place. So let's try and build a tool to find them in the first place that's open source, and then we can move on to things like this that are maybe a little more interesting, a little more detailed. Another thing that you can do, this is something that I was done with a collaborator, is look at super resolution, right? So especially with satellite imagery, where things are often very blurry because they're so small, if you super resolve an image, does that help you, right? Maybe it looks prettier, but we're not watching Hollywood movies here. We're actually trying to look at analytics. Does it help your object detection, or is it just to make it prettier? And what we found actually it does help you at the higher resolution. If you look at really low resolution imagery, it doesn't help you much. But if you look at the sharper imagery, making it even sharper, that seems to help. So that is kind of fun. And then finally, I mentioned buildings. You can actually you can make an attempt to find the rough outlines of buildings with this tool. I'd say rough because, as you guys know, most buildings aren't perfect rectangles oriented north and south, right? And so what you really want to do is get a precise polygon for that building outline. That's something we've worked really hard at for SpaceNet. But if all you care about is a rough outline of the building location and area, there's something you can do pretty rapidly. That's what we're showing here on the right, of pulling out the building footprint bounding boxes in blue. You can also pull out other infrastructure like transmission towers. That's what we're showing in the left image there in green. We're pulling that out with a model trained to find that. This is all SpaceNet imagery here. So now I have a demo that let's hope this goes well. I mentioned before that we have this car data set that's pretty good. So this is a data set that's put out by researchers at Lawrence Livermore, and it's about 30,000 annotated cars, 15-centimeter resolution aerial imagery in 6 locations in USA, Canada, New Zealand, and Germany. Train a model with this data to locate the cars, and then we're going to apply it to data from the Zanzibar Mapping Initiative, another open source data set that's mapped most of Zanzibar. No labels there, just imagery. But it's 7.5 centimeters, so we actually have to downsample the imagery to get approximately the same resolution to fit in the model. But clearly here we've trained a model on one data set, one sensor, applying it to another, and we'll see how it does. So let me see if I can get this demo up and running. I'll spin up the Docker container. So we put this all up on GitHub. So I'm just logged into my cluster. There we go. So now in a Docker container for Simmerdown, let's see what hardware we're working with here. So in this case, just a single Titan XP GPU, right? So this is very consumer grade. I just looked it up. They're $1,200. Just one of those 12 gigabytes of memory. Pretty standard. Nothing super fancy there. And what we're going to do is we have this model that we trained to find cars on this COSMIQ data. We're going to apply it to this other data. This is just the command here to load that model and run it. So I'll copy that in, and let's fire that off. All right, so loading in the model, and now we're processing through the imagery, right? So this data has been kind of pre-chunked, which is something you would do anyway, because if you want to say run a map tile server, you'd have these things in little smaller chunks, but it can still read in a massive image. So we're iterating through all these small windows as we go. It's running at around 80 frames per second, which translates to maybe around 20 square kilometers or so per minute. So there we go. We went through, that's all the GPU time. We're adding in the geo-coordinates now, doing some non-max suppression, and all right, there we go. Ran that for this image. It's about an 8 square kilometer image. All right, I'm going to just copy this locally to inspect. Let's hope the internet behaves. And then I will open this in QGIS, which is just it's a pretty powerful open source software that lets you inspect and label imagery, the large geospatial images. So once this is done, yeah, we'll get there. Yeah, so the slowest part here is transferring data, apparently. That's not so bad. And then I'll just inspect it locally. So once this is done, and there we go. Let's open up the image in QGIS. All right, so here's the image we just put in, right? Again, about 8 square kilometers drone imagery over Zanzibar City in this case. This is the imagery that we're dealing with. Pretty interesting structure in this imagery, I'd say. All right, so now let's load the outputs of our Simmerdown model that we just ran. And let's change this color scale, something that's a little easier to see, make it somewhat opaque. There we go. All right, so now we're overlaying all the car detections on this test imagery. And this is what we get, right? Of course, wouldn't claim it's perfect, but this is doing a decent job. Remember, there's only cars in this test or training imagery, so things like buses are not actually expected to be detected, right? So things like this are actually not a false negative that shouldn't be detected. But again, doing a decent job. Don't have any metrics here, unfortunately, so this is just pretty pictures. There's no ground truth. But this is just an example of what you can do with this tool. In this case, there's about 5,000 cars in this image. We pulled this out in less than a minute. And then we can inspect georeferenced data points for this data. All right. So that's basically it. I wanted to end on that demo. Conclusions, right? Object detection is still tricky with satellite imagery for a number of reasons, primarily being the large scale you have to deal with. We've kind of demonstrated Simmerdown is one option you could use to find objects at scale. We've shown it can find infrastructure and vehicles, and we can process arbitrary large image sizes pretty rapidly, 20-ish kilometers squared per minute per GPU, right? With just one GPU here. It's all open source up on GitHub, continually updated with new TensorFlow models for that part of it. And if you'd like to know any more, feel free to look up our GitHub. SpaceNet Home is SpaceNet.ai. Data is on AWS, free to download for a SpaceNet. We're pretty active on our blog, and we have podcasts and Twitter as well. Thank you.